Jnanam Paramam Dheyam. Knowledge is supreme.
So far, we have discussed the background that is required to now enable us to understand what microwave spectra look like and why. Okay. One thing we have said already is that the separation has to be equal. Why does it have to be equal? Because the selection rule is delta j equal to plus minus 1, epsilon j is b j into j plus 1. So, of course, epsilon j plus 1 would be b into j plus 1 into j plus 2. So, if I write nu bar is the wave number, or one way of writing the frequency of transition for j to j plus 1, that turns out to be how much? 2b into j plus 1. Is that right? So, where will the first line, where do you expect the first line? Do you expect the first line at 0? See, it cannot be 0, isn't it? Because if there is a transition has to take place, delta m is 0, delta j is what matters. It cannot be 0, right? Because if a line occurs at 0, that means there is no transition, isn't it? So, first line occurs at put j equal to 0, j equal to 0 is the smallest value anyway. First line occurs at 2b. What about the next one? Yeah? Then somehow I managed to invent a new numero letter, new alphanumeric character. Next one 6b. So, there is no point in working out each and every one of those. We understand that they are going to be equispaced. And so on and so forth. Great. Okay. Equispaced for what kind of rotor? Do not forget, for a rigid rotor. Before we finish today, we hope to introduce the energy expression for energy for a non-rigid rotor, and then I will leave it to you to figure out what the spectrum of a non-rigid rotor is supposed to look like. All right. Then, so y axis, x axis is defined. Now we have to worry about the y axis. What do you have on the y axis? Intensity. What does intensity depend upon? It depends upon the intrinsic probability of transition. If you want to put it in terms of something that is experimentally observable, that would be your epsilon, right, molar absorption coefficient. So, let us for the moment assume that molar absorption coefficient of each transition is the same. All delta j equal to plus minus transitions are equally probable. Let us just assume this. Later on we will come back to it and see whether it is absolutely correct, or whether it is correct to an extent that we can live with it, or whether it is an absolutely wrong assumption. Okay. For now, let us go with it. So, then the only thing that is left is population, right. If you have more, if you have a line arising out of a greater arising out of a level with a greater population, then by brute force it would be a more intense line, right. So, now we have to worry about population of the jth level. Population of the jth rotational level. Now, I believe you are familiar with Boltzmann distribution. What is Boltzmann distribution? Well, ratio of two levels, population of two levels is equal to degeneracy multiplied by e to the power minus delta E by kT, right. So, I can write like this, Pj is proportional to, what is degeneracy of each j level? 2j plus 1, we are all confident about that. 2j plus 1 multiplied by e to the power minus Ej divided by kT, isn't it? So, let me write the expression for Ej. What is the expression for Ej? Bj into j plus 1 divided by kT, is that right? Well, generally you do not write kT in centimeter inverse. So, it is better to convert epsilon j to Ej. So, you have to write Hc here also, that is why I left the gap. So, minus Bhc into j plus 1 divided by kT, okay. Before we go ahead and discuss this, let me digress a little bit and ask you a different question, which will not tell us anything about the spectrum, but it is a fundamental question about rotational levels. What is the energy of the lowest energy level of rotation? For j equal to 0, what is the energy? 0, right? 0, which means the molecule is not rotating. If it is not rotating, then its energy is 0, plus minus 0, right, and no potential energy, only kinetic energy. So, momentum is 0 plus minus 0, right. So, no uncertainty in momentum, right. But then if it is fixed, then uncertainty in position. What is uncertainty in position? Wait, yeah, why? Well, you are right. What you are saying is uncertainty in position is infinity. That is why uncertainty in energy is okay. Uncertainty in momentum equal to 0 is okay, right. But can you explain to me why uncertainty in position is infinity? Uncertainty in position is absolutely uncertain. Why? Yes? Yeah. Well, you do not know what is theta and you do not know what is phi, isn't it? Theta can be anything from 0 to 180 degrees, right. Theta can range from 0 to 180 degrees, and in this case theta can be anything from 0 to 180 degrees. So, it is uncertain completely over the range of theta. Similarly, phi can be anything, okay. That is why it still does not violate uncertainty principle, okay. Well, this is the wrong CH107 batch to ask the question, because I think we asked you this problem in quiz or something like that, and I think to your rights also know this. Please remember, because when we talk about vibration, we are going to discuss 0 point energy, and we are going to say that for vibration energy can never be equal to 0, because then uncertainty principle is violated, okay. We will discuss it at that time, but for rotation it is okay. It can still stop because you have complete uncertainty about theta as well as phi, okay, good. So, now we come back to what we were actually discussing. Population of the jth level is proportional to 2j plus 1 e to the power minus Bhc into j plus 1 divided by kT. If I want to find out what is the level with maximum population, how do I do it? Yes, even before that, are the higher levels at all occupied? That is an important question. What is the typical energy gap between, say, j equal to 0 and j equal to 1 for, well, we are talking about microwave spectroscopy, right. So, what kind of energy are we talking about here? It's say 5 centimeter inverse, 10 centimeter inverse, no more than that, right. So, for this kind of energy gaps, higher levels actually get populated at room temperature, okay. So, it makes sense to talk about a higher population of the higher J levels as well. So, this is what it is. So, dPj dJ has to be equal to 0 for J equal to J max. J max means the J level with maximum population. Okay. What is dPj dJ from there? What is dPj dJ? One thing I know is that this will definitely come out, e to the power minus BHC J into J plus 1 divided by KT. This comes out. If I differentiate the first term, then I get 2. If I differentiate the second term, then I get minus BHC divided by KT multiplied by J square plus J. So, it is 2J plus 1. Is this right? Is this dPj dJ? Just check if I have made any mistake. Sushnata? Of course, you have to work it out yourself if you have to tell me whether I have made a mistake or not. Let us do it quickly. Easy differentiation, right? E to the power minus BHC into J plus 1 by KT, that comes out anyway. Yes, sir? Why? Yes. So, what will it be? Will it be 2J plus 1 whole square? Yes. So, see Sushnata, you have to work it out, otherwise I can make a mistake and I can teach you a wrong expression, okay, and you live with it for the rest of your life. That is not so good. So, when I work out something, you also work it out. Do not think I will always do it. More often than not, I make mistakes. So, is this okay now? Yeah. So, when J equal to J max, then what happens? This should be equal to 0. Okay. If this is equal to 0, then what happens? This I do not have to worry about. What I write is 2 minus BHC divided by KT into 2J max plus 1 whole square is equal to 0. Is that right? So, please do it yourself. Please do it yourself independent of what I am doing, so that you can tell me whether I am right or wrong. So, 2J max plus 1 whole square is equal to 2 KT by BHC, and then we have 2J max is equal to root over 2 KT by BHC minus 1. So, J max equal to root over KT by 2 BHC minus half. Yeah, right? Is that right? Question? Okay, why the 0th level is not maximum populated? Because first of all, if I do not do all this, if I just look at this population, what do you see? 2J plus 1 multiplied by e to the power minus BHC whatever, right? So, this exponential term is a decay, right? What about this? It is a linear increase with respect to J, isn't it? So, you multiply a rising straight line with an exponential decay, what kind of curve do you expect? It goes to a maximum. Okay. So, that is the answer that I get from simple algebra or geometry or whatever it is. Huh? I'm drawing pictures, so maybe it is geometry. No, it is algebra, just plotting. Okay. And otherwise, if you think of, well, the same thing, Boltzmann distribution. So, if I write Pj divided by P0, okay, what will it be? So, just subtract right. And then here in instead of E you have to write delta E, that is all. And what is delta E? What is the energy of J equal to 0? You just told me it is 0, isn't it? So, same expression. So, in what we see is that the ratio actually goes to a maximum. So, since the energy gap is small, if I think physically now, the room temperature is enough to cause a promotion. Suppose do a thought experiment. Let us think that there is no rotation. We start with a situation like that somehow, and then we expose it to the room temperature. The temperature will be enough to cause a redistribution of the population, so that the upper levels also get populated. So, as you go higher the levels, the factor that affects the factor that favors population of higher levels, of course, is degeneracy, right. There are more levels at any given energy. The factor that disfavors population of the higher levels is the energy gap. So, the temperature will not be enough after a while, right. That is why it will eventually fall off. Are you answered? Okay. So, this is your expression for J max. What is the problem with this approach? Okay, Shivam, tell us. Okay, I'll say perhaps that is what you are trying to say anyway. See, when do we do differentiation? When you have continuous curve, right? Right? Do we actually have a continuous Pj versus J curve? We don't. We have Pj values for discrete J values. Okay. So, we are kind of extending the scope a little bit. So, the answer that we get, do you think this answer will always be integral? No, right. So, you will get something like 3.2 or 10.5 or something like that. But actually J max has to have an integral value, isn't it? So, from this approach you are only going to get an approximate value which will usually have which will usually not be an integer. So, what you need to do is you need to take the nearest integer. If you get 5.8 from here, then the correct answer is 6. If you get 10.2, then the correct answer is 10. If you get 9.5, then I do not know what the correct answer is. Yes, Shushnata. Actually, yes. So, most likely it is 6, well somewhere either 5 or 6. At least we can zero down upon where the maximum will come. Okay. But what we learn from here is that the spectrum is going to look something like this. Okay. If it follows the population of the levels of origin of transition, is going to go up and then come down. Of course, the discrete line spectra will go up and come down. Okay, so far so good. Okay. Now, in the remaining 9 minutes that we have today, let us try and understand a little more finer detail about the spectra. To repeat something we have done already, what is the molecular property about which we can get information from this spectrum? Bond strength, bond length, not bond strength. Bond strength comes from vibrational spectrum. Bond length. Why? Because each of these gaps is 2b and b is, what is b? H by 8 pi square mu r0 square c. The only unknown is r0. R0 is basically the bond length, right. So, we can actually determine bond length. And now let us see how the spectrum would be affected by two different factors. First of all, continuing with the discussion that we had a little earlier, suppose I record a microwave spectrum at room temperature and then I record microwave spectrum of the same molecule at say 500 degrees centigrade. Will they be same? Will they be different? Okay, I am assuming that rigid rotor holds in both the cases. I am assuming bond length does not change. If the bond length changes as a function of temperature, then of course your spacing will also change. But if I can assume that bond length does not change, then spacing will remain same. What will change? Intensity of spectral lines, how will it change? Yes. So, this maximum J max will move to higher value, isn't it? If I increase temperature, then I can expect that J max, the line, the J value for which we get the most intense line will move to higher values. Okay? So, I can expect what kind of a shift is it? A shift. So, I can expect the entire spectrum to undergo what is called a blue shift, right. Blue means higher energy, red means lower energy. Okay. So, it's the other terms that are used are hypsochromic and bathochromic shift, but that has been my Achilles heel or whatever it is called, Achilles heel. Ever since my college days, I have never been able to remember which one is bathochromic, which one is hypsochromic, and why will I unnecessarily use such big words when I have simple blue and red at my disposal, right. So, if you want to use bathochromic and hypsochromic shift, be my guest, I will always say blue and red. So, at higher temperature you expect microwave spectrum to undergo a blue shift, at lower temperature you expect it to undergo a red shift. That is point number 1. So, we have discussed the effect of temperature. What do you expect with temperature? You expect some spectral shift. Now, we will talk about something else. If you look at the same microwave spectrum, let us say we are talking about HCl, okay. You expect a spectrum that looks something like this, okay. If the resolution of your spectrometer is good enough, then what you see is each line looks something like this. Each line turns out to be a doublet. I am talking about HCl and I am addressing a class primarily of chemists. So, can you tell me why? Exactly. Chlorine, what is the atomic number of chlorine? 35.5. Why is it 35.5? Because it is a mixture of two isotopes, right? Yes, 37 and 35, no 0.5 there, 37 and so, now see what happens. It is not only R0, you also have mu, isn't it? So, if you have two isotopes present, then you actually have two kinds of molecules with two kinds of mu's. For that, you are going to get different values of B, isn't it? So, every line will actually consist of two lines, okay. So, if you have a high resolution microwave, if you can do high resolution microwave spectroscopy, then you can get an idea about isotopic abundance. Okay. Before we discuss non-rigid rotor, that is where we will end today's class with. Let us just think for a while with this background, for what can these spectra be used? What can be possible applications of microwave spectroscopy? One thing I have already said, right, you can identify bond, you can determine bond length. What else? Well, one application is something that is now absolutely commonplace. I am sure everybody has used, if not at home, then definitely in the hostel. Everybody has used a microwave oven, right? How does a microwave oven work? Yeah? No, see, all along so far we have talked about rotation, there is no question of vibrating here, okay. And I do not know why, but whenever I ask this question to any audience, including people who have completed MSc and have come to us to do PhD, everybody says, talks about vibration. It is not vibration, it is rotation, yeah. Rotation of water molecules, right. So, see, the point is this, remember one thing that we understood is that the molecule has to be dipolar, and unless you are somebody who survives on eating steel, all the food that we eat has 70% water in it, as Madhuri Dixit madam has been telling us for last few years over TV, right. Even we are 70% water. So, what happens is when you put the food inside microwave oven, water your oven typically has microwave radiation that is absorbed by water. So, all the water that is there inside the food, water molecules, they start absorbing microwave radiation and start rotating, not vibrating, please remember, rotating. But then they cannot rotate forever, right. They come to a stop because of dielectric friction. Other molecules are there, water molecules, other water molecules and non-water molecules around. They cause these water molecules to come to a stop. But then all that energy has to be dissipated, right. Where does it go? Yeah, all around. And that is why the food gets heated up so quickly in a microwave oven, because now you do not need a fire from outside. The fire, if you want to call it, is within. And as you know, things are more efficient when the fire is within, right. So, that is the reason why microwave oven can provide such efficient heating. But the point to note is that using a microwave oven, you can cook fish, but you can never fry fish. Why? Because if you want to fry fish, then you have to heat oil, right, you have to go to a higher temperature. But oil, if you keep oil for even 100 years inside a microwave oven, keeping the oven on, oil will never get heated, right. Oil is completely non-polar. So, you cannot fry things, okay. Now, before we end, hold on, we are not done yet. So far we have been pretending that molecules are rigid rotors, okay. Such an approximation is always too good to be true, okay. We are saying that when the molecules rotate, we do not have to worry and all, but actually we have to worry. Molecules are usually non-rigid rotors, non-rigid rotors. Why are they non-rigid rotors? Because when they rotate, one thing that can happen is that due to centrifugal force, the bond can become a little bigger, centrifugal distortion, right. So, what will it affect? It will affect the average value of R0 square, okay. So, what happens to the effective value of B? If R0 square becomes bigger, B becomes a little smaller, right, if you can think that way. And if you think in terms of perturbation theory, now we are introducing non-rigid rotor. This is something that I will ask you to study by yourself from Banwell's book. We will not do the entire quantum mechanical treatment. So, you only need the results, that is something you can understand if you just read Banwell's book. But the point is epsilon j is now written as Bj into j plus 1. Well, this is the expression for the non-rigid rotor, right. Now, that is the unperturbed system. You have studied perturbation theory and you know that whenever there is a perturbation, what is the meaning of a perturbation? A small change, right. If the change is huge, then perturbation theory does not work, right. If it is small change, then what you can do is you can start with the original value and bring in correction terms, right. And the first order correction term, keeping in mind that energies have to decrease a little bit, is d j square into j plus 1 whole square. So, you see this correction term becomes more and more important as you go higher and higher up the energy ladder, which means the molecule is rotating with higher energy. That is why centrifugal distortion is more. So, I leave it to you to work out the expression for nu bar for j to j plus 1, and I leave it to you to figure out how will it affect. So, what is this and how does it affect the microwave spectrum? What is the spectral signature of non-rigidity?